and share my screen for real and come over here. Okay, and load those tabs. So last time we were talking about indexes and making SQL queries fast. And yesterday your Twitter Postgres assignment was due. The new Twitter Postgres assignments been posted. We're going to start today going over what to do for the new homework assignments, and then we'll finish up today going over more things related to indexes. We probably won't finish everything that we need today for the indexes, and so Friday I'm expecting we'll do another lecture on indexes on Friday, and that'll be the last of the main lectures for this course. Sometime before the final exam is posted, I'll have, we'll use like just the normal class time period, but we will have a chance for like a review session on the final and getting any questions that people have answered about the final. So yeah, the plan is today, class Friday, and then one or two classes some point over the next 2 weeks at a time to be determined. Any questions about administrative stuff for the class? Hmm? So yeah, the baby's due date is over the weekend, so probably I will start the paternity leave over the weekend, and so probably not be here on campus next week at all, but then yeah, maybe either Wednesday or Friday next week or Monday the week after, having the review session for the final exam. Okay, the indexes assignments under, so I posted a new topic 11 folder here of the advanced indexes, and under here there's a link to the Postgres indexes assignment. If you click that link, it will take you over to this GitHub repository, and there's a lot of things going on in this GitHub repository. We'll take a high-level overview look about what to do, and then after today, we probably won't have covered everything that you'll need for the assignment, but you'll definitely be able to get started with it and complete like 80% of it. First thing to notice about this assignment, there's two services inside of here, the denormalized and the normalized batch. These two services are identical to the services from your previous parallel loading assignment. The normalized batch right here is my solution to the previous assignment with the modified SQL schema that makes it so that you can load stuff in parallel without getting the deadlocks. If you haven't fully finished the previous assignment, then I'm trusting you not to start this assignment copying these solutions until having finished the previous assignment. Inside of here, there's a SQL.normalized batched file here that has these 5 SQL queries. And if you take a look at what these SQL queries are doing, they're doing things that are similar to, or doing computations that are similar to what your Twitter Postgres MapReduce assignment was doing. So here's counting like the total number of times coronavirus was used as a hashtag, and then some more complicated queries going on. And we're going to need to be writing indexes to speed up all of these queries. The actual data that corresponds to this assignment is we're going to be using 10 full days of Twitter data. So it'll be the same 10 days from the previous assignment, but now the zip files aren't truncated. It's not just the first 10,000 tweets, but all 4 million tweets from each day. So because it's going to be relatively large, there'll be a few special instructions about preparing the repo and some special debugging tips that we'll go over. So the first thing that you'll need to do is you'll need to just make sure that that you bring everything down from your previous assignments. And then you'll be modifying the Docker Compose file again, adjusting the ports like you've been doing and bringing it up. That's all relatively the same, but step 4 here is going to be new. That you'll notice, I'll open up the Docker Compose, and I don't have my terminal anymore, so I'll open one up really quick. 46, not 46, 143. And cd project Twitter Postgres indexes inside the Docker Compose.yaml file. Our volumes here now, we're not using the named volume. So previously inside of our services here for Postgres, there's always been this volume here. This is again a bind mount. When you have a path to the left of the colon, the bind mount tells you a location on the Lambda server to map to the database. This bind mount, this top one, is the same. This just means that you'll have access to the SQL files or code that you change on the Lambda server inside of the database. This one's not too important, but down here, this one is important. What this one is telling us is that the location that it's going to be storing the Postgres data is going to be at this location in your home folder. So home/bigdata/pg denormalized. And all your home folders this morning, I created a new symlink called Big Data right here. If you go to your home folder and type ls-l, you'll now have this symlink right here, Big Data, which links to this other location over here. And inside of the Big Data folder here, you're allowed to create up to 250 gigabytes of storage. Inside of your regular home folder, you only have 10 gigabytes of space allowed. For this assignment, you're going to be having to create around 200 gigabytes of data between all of your Postgres databases. So that's why things have to be inside of this Big Data folder. The Big Data folder here is linking to this /data location, which is stored in the HDDs, the hard drives, instead of the NVMe drive. And so all of the data access will be slower inside of the Big Data folder. The main difficulty, so these next few paragraphs here are just summarizing what I just said. The main difficulty here with this Big Data folder and how these bind mounts are being created is that if you look at the contents of the Big Data folder, after you bring up the database and create the databases, you'll have these two folders inside of it, PG denormalized and PG normalized batch. And these two folders right here are things that are not going to be owned by you. And because they're not owned by you, you're not going to have permission to delete them if you make a mistake. The reason they're not owned by you is because they're owned by the root user of the Docker container. So after you bring up your Postgres databases, if you run these commands right here, you'll get output that looks like this. This will be your username right here. And this number over here will correspond to the user ID that Docker is using to create your databases. So if you make a mistake loading the data, which is very easy to do now that both of these do not have like the unique constraints inside of them. For example, if you accidentally load some data multiple times, you're not going to get the correct results in your SQL queries, and you'll have to delete the database. And you can't do that using normal terminal commands. You also cannot use that using the Docker volume commands, because Docker volume only works with the named mounts and not the bind mounts. And so you'll have to be using these special commands down here that I've provided for you. That it's going inside using Docker Compose, going inside of these services and deleting the actual database from inside of the service. That's not the only way to delete the folders, but that is the simplest way to reset your database. So these are the two commands down here to run if you have to reset your database for whatever reason. And again, the most common reason for needing to do this is because you're running your check answer script and you're not getting the right answers here because you have the wrong SQL data loaded somehow. There are ways to complete the assignment. If everything goes correctly, you won't have to run these commands down here, but probably for the vast majority of you, things will not just go correctly. And so you will have to run these commands at some point to reset everything and start over from scratch. Any questions so far about how the data is being stored or resetting the assignment if you need to? Okay, in terms of actually loading the data here, so I've provided my load tweets parallel.sh file that you can just run, and you'll run that and it will load the data for you. Some notes here on the disk usage. I think so we've talked a lot about the different advantages of the normalized versus the denormalized representations. Another disadvantage trade-off that we haven't talked about too much is the disk usage. Here that you'll see in the denormalized database right here, if I run the disk usage of the PG data folder, it will give me 75 gigabytes being occupied for the denormalized database and only 25 gigabytes being occupied for the normalized database. So the denormalized database, one disadvantage of it is that it's using 3 times the amount of disk space as the normalized version down here. So in total, with no indexes being created, you're going to be using 100 gigabytes. And then as you're creating your indexes on the data, you'll be using about another, I think my solution uses about 50 more gigabytes of data and indexes. But yours might potentially use more than that. The actual data itself, if you look at the raw data files, it's only 17 gigabytes of compressed data. So even the normalized representation still adding a little bit of overhead over just these zip file representations. Again, I guess the main takeaway on this step 1 right here is that this is just what your previous assignment was, load tweets parallel, but now it's actually loading lots and lots of data instead of just 10,000 tweets. Maybe a good thing to highlight down here is the runtime here. So 1,500 seconds and 23,000 seconds is how long to expect it to take. Any questions on loading the data? What to do, what to expect? Okay, then the actual assignment here, step 2, creating the indexes. You're gonna, for the normalized database, all you have to do is create indexes so that the queries are fast. I already have the 5 SQL queries provided for you. 1, 2, 3, 4, and 5. If you have no indexes on these queries, then the runtime takes about 2 minutes to do everything. They all just reduce to a sequential scan on the table, and so it takes 2 minutes to load that 25 gigabytes of information from the hard drive and process it. And you should, after loading the data, you should get all of these things passing without creating any indexes on it. The main task here will be to create the indexes so that they run fast. And my solution, after I have created my indexes, this is what the output looks like. And now everything goes from 2 minutes of runtime down to 3 seconds of runtime. And for grading purposes here, the way your grade will be determined is that this assignment here, or this part of the assignment, is worth 16 points. If you get your runtimes down below 4 seconds, you get full credits. And then for each second above that it takes to run, you lose 2 points. So the slowest you can possibly be and get any credit at all is, what is that, 12 seconds. Take a look up here at these SQL queries. So it's under this SQL normalized folder. And what these queries look like. The first queries, they basically go from simplest to most complicated. And this query right here is going to be just a simple btree on the tweet tags table with the id tweets column. That will allow you to do this as an index only scan. And the distinct will I don't think we explicitly talked about the distinct operation here yet, but in order to do a distinct, it has to do one of the aggregate functions, and we'll want it to do the group aggregate. So having everything be sorted from an index only scan will make the distinct here fast as well. The more complicated ones down here, you get some fairly complicated queries that you'll have to think about, like joins and all the different explicit group bys, order bys. Here we have ordering by multiple things, the limit. And so thinking about how do you first identify what is the algorithm that you're trying to achieve for each of these operations, and then writing those SQL queries that are going to achieve that. The main thing index-wise that we haven't talked about yet is this @ operator. And so after we finish talking about this assignment, we'll talk about this @ operator rest of today and Friday in class. But otherwise, these first 3 SQL queries up here, things that you should be able to complete at this point, and then 4 and 5 after Friday, you'll be able to complete. Any questions on what's expected for that first, or for the normalized database, this step 2? Okay, then step 3 down here. Oh, maybe one last, I don't know, there's a handful of various hints and things down here. This last one I will highlight right here, that creating an index under the default settings of Postgres will take up to 30 minutes, depending on exactly what the index is that you're creating. And this is because by default, Postgres only uses a single core when it's creating an index and only 20 megabytes of memory. So the data is much bigger than 20 megabytes. So this is not fitting into data. So it makes things slow down considerably. Your user accounts have permission to use up to 80 cores and up to 16 gigabytes of memory. And so you're not required to change the settings of Postgres to take advantage of this. But if you do change those settings, then your indexes will create much faster in just say 1 minute instead of 30 minutes. And this link down here gives you instructions on how to change the settings so that Postgres will take advantage of this. So you're not required to do that, but I would definitely recommend changing this so you get the faster iteration time to see if your indexes are being effective. Another tip for checking if your indexes are being effective is to not build your indexes on the entire data set, but build your indexes on the small data set that you were inserting with the previous assignment, so that then it's only 10,000 tweets. So the indexes will create very fast in just a couple of seconds. And you can test to make sure that it's using the correct index scan algorithms with that small data set. And then once you have it all working, then you delete the small data set with these operations here, insert the large data set, and test your runtimes. So a key part of this assignment is just going to be getting a good workflow going so that you can test your indexes quickly, because they will be created quickly. Last step here, step 3, is working with the denormalized database. You're going to have to do 2 things for the denormalized database. The first is you'll have to actually write the queries, write the SQL queries. And so up here, again, in this SQL normalized folder, I have the normalized version of the query that's not considering the JSON. You will have to create a SQL denormalized folder with corresponding 5 queries for the denormalized database that do the exact same things as these queries here for the normalized database. Then after you have those test cases passing on the denormalized database, you have correct SQL statements for the denormalized database, then you'll create the corresponding SQL queries, or sorry, the corresponding indexes that will make those queries fast. So this is going to give you practice both for writing queries on the denormalized database and practice of writing queries and indexes at the same time. It'll turn out that there are many ways that you can write those queries. Some of them will be easier to write indexes for, and some of them will be harder to write indexes for. And so that'll be, again, some of the material that we'll be covering today and Friday in class. The grading for this this second part of the assignment is that in order to, so it's also worth 16 points. In order to get any of those 16 points, you first of all must have all of your test cases passing, so that all of the SQL must be correct in order to get any credit. And then after the test cases pass, then the grading will be the same as with the normalized database, that you have 4 seconds to complete everything to get full credits, and each additional second you take results in 2 points being taken off of your score. My solution here, my solution on the denormalized database, if I have no indexes, takes 40 minutes to run all of the queries here. It takes 40 minutes, but after creating the indexes, it takes 3 seconds to run the queries. So very, very big performance difference. And the this number here, the 40 minutes on the denormalized without the indexes, is way slower than for the normalized database. For the normalized database, it was only 2 minutes. But once you have the indexes, doesn't matter whether you're in the normalized or denormalized form, you still get the very, very fast runtimes down here. One last aside comment is that actually most of these 3 seconds of runtime are shell script overhead, part of the test case passes over here. My actual queries themselves are running in under 100 milliseconds in both cases. So the actual like runtime of doing this is basically free, basically nothing, and these are all things that you could cheaply embed into a web page and nobody would notice that, or the overhead of doing these queries would not be noticeable to an end user. Submission. I've got your commands down here to actually run to report what your runtimes are and test cases. You'll run these commands. It will create these results files. You'll add those results files into the into your GitHub repository, and then just submit the link to Sakai. There's no test cases on GitHub to pass because we're not uploading all of these hundreds of gigabytes to GitHub. So I'll just be looking at these files created by these 2 commands right here in order to do the grading. Any questions about anything for the homework? Okay. Then we will continue with our discussion of indexes and the notes file. I don't have it open anymore, so let me open up our notes file that we were working on previously. There we are. File open. And it is the questions_in_class.pdf file that we're working with. And last time where we left off here was we were talking about the join algorithms and what are the indexes that you needed to create in order to make this particular SQL query right here fast. And with join algorithms, there's a special or an extra thing that you have to consider, and that's that the join algorithms are they only consider two tables at once, but we can join an arbitrary number of things together. And so we have to, when we're creating our indexes, we have to create indexes for all possible join situations, whether we first join, in this case up here, users join tweets, and then take the result of that and join tweet tags, or whether we do the reverse, take tweet tags, join tweets, and take the result of that and join users. And so down here, I have all of the create table or create index commands that we talked about for both of those two situations. These top ones up here are the first parenthesization of users' tweets followed by tweet tags, and the bottom one down here is going the other way, right to left, tweet tags and tweets first, followed by users. In this problem too, at this point, we were only considering doing the joins by themselves, not considering how to take into account this where clause down here or this group by clause down here, or the fact that there's the count star up here. So we'll reconsider this problem, taking into account these extra steps next. For the joins, before we get to the taking into account the where and the group by, for the joins, the algorithm that the best case algorithm that we were trying to target was the merge join. The merge join required that the inputs be sorted, and so we were creating indexes on all of the columns that we're doing the join on. So up here in orange right here, when we have create index on users, id users, create index on tweets, id users, that corresponds to this join right here between users and tweets on the id users column right here. And these indexes right here will allow us to do the index scan or the index only scan, getting the results out in sorted order so that we can use the merge join to group these two things together right here. Once we have these results, there's no way for us to get the result of the merge join in sorted order according to the id tweets down here. And so we're not going to be able to use a merge join to combine the orange with the red down here. And we needed the nested loop join to do that. And this red index down here allowed us to use that nested loop join with an index search on the inner version of the loop. Okay, that's where we left off. That was a very quick review, very high level overview of things. Before we move on though, any questions about what we talked about last time, what we've done so far? Okay. Yes.
So after you get the first two,
the orange ones?
yes.
Mm-hmm.
So in demand, that means you get
so it's not the index that gets us the new table, it's the join here between users and tweets. That'll give us a, right.
Yeah, so if you get the X generating would you get another index?
So the question is, here I'm creating an index on tweet tags. Is it possible to create an index on the join of users and tweets right here? And the answer is no. In general, when you create an index, you can only have a single table out here to the left of the parentheses over here. And so there's no way to create an index on a join result. It would be possible to actually create a new table from scratch, fill that new table with the results of this join over here and create an index on that new table, but there's no way to automatically keep that new table up to date with the join over here. So people do that in order to speed up joins, but it results in a lot of very complicated sort of bookkeeping work to keep that new table up to date. And it also results in a lot of disk space overhead because of you have to keep all that information duplicated and the duplicated indexes. In general, vast majority of times, it's not worth the effort of doing that. Did that answer your question? Cool. Yeah, that was a good question. Let's see. How does everybody feel about the join algorithms? Like easy to understand, zero understanding, somewhere in between? So little understanding, it's impossible to respond. That's a fair enough place to be at this point. Again, this is the stuff that you'll need in order to complete this this indexing assignment and also for the final exam. And again, historically, students have found the final exam much harder than the midterm exam, or at least grades are significantly worse than the midterm exam. I think it's in part because these things are just very abstract. So yeah, it's okay if at this point everything's not fully making sense, but it will need to make sense before working on those two assignments. So down here, under these 6 indexes that we've created, you'll notice that some of these indexes are duplicates of each other. So like this id users up here, id users down here, duplicates, this tweet tags, it tweets, tweet tags, it tweets, duplicates, and these middle ones up here, the only ones that are not duplicates. And so a full credit answer does not need to report all the duplicate indexes. You can just report the 4 that are unique. We're going to modify this now, though, to take into account this where clause right here. So how do we take into account the where clause? Well, where clauses, the most efficient way to do them is to always do them before doing the joins. So before joining here, if we consider this this bottom case where we're joining tweet tags with tweets as our first join operation, tweet tags with tweets. Before doing that join, if we filter the tweet tags so it only has the appropriate tag inside of it, then there will be much fewer things to join here, and so the join will be faster. So we want to construct our index so that this where clause can happen before the join happens. In order to do that, the columns that we'll be considering in our where clause will have to come before the columns that we're considering in our join operation up here. Here, when we're using this, this like operator, this is one of the operators that the btree can speed up. And so we'll want to put this, the tag column over here in front of the id tweets inside of our create index command. Where is my, there we go. So the way to modify this in order to take advantage of this, this where clause right here is to put the tag inside of our tweet tags right here and putting it in front of the id tweets column so that we can first filter out all of the tags that match our prefix and then have everything remain in sorted order on id tweets down here so that we can do the merge join on combining these two things together. Yeah, it's important that the tag is to the left over here because we're doing an equality search on the tag. And so we'll do that thing first. Whatever the operation is that's coming first is the thing that needs to come first in your index creation statement. And then the id tweets over here as the second operation. If we were doing the version of the SQL query up here, where we are first combining users and tweets and then combining with tweet tags down here, then the same situation applies, where we will want to do the filter down here before applying the join operation. So up here, we would still just add the tag operation before, or the tag column before id tweets, and that would let us take advantage of the where clause. In both of these cases, we'll be able to do an index-only scan of the tweet tags table because we need two columns in order to do the where and the join, the id tweets and the tag, and both of those columns are contained inside of the index, and so we'll be able to do the index-only scan. Yes.
Usually, I put where clause comes after
The where clause comes after what?
after I've created on the table.
So the physical location of the where clause in the syntax of the SQL query is that it comes after the join clauses and everything else. But this SQL is a declarative language. It is not a sequential language. It is not a procedural language. And so Postgres will decide to perform this where condition wherever it is most efficient to do so. If we have an index, it will be most efficient to perform the where clause filtering before doing the join clauses, because that will make the joins go faster because there will be less data to join. If we do not have an index, it will probably be most efficient to do the where filtering after doing the joining, because the joining will remove some rows as well. And then we would do a sequential scan over the results to filter out the where clause down here. So just because like the physical layout of this where clause is after everything else doesn't mean that the algorithm that Postgres will actually use to implement it will happen afterward. Did that answer the question? Yeah, good question. Mm-hmm.
Doesn't have, so we are creating two
Mm-hmm.
Does that solve the process of joining?
Does this solve the process of joining?
Solve the process of
Sort the process of joining?
slow
Slow the process of joining. This is a good question. So basically the question is, what are the disadvantages of having too many columns inside of your index? There's many trade-offs with adding more columns in the index. One is, so in this case, the ultimate answer is that this will be faster because this will be able to remove many of our rows from the data set. And ultimately what we want to do is remove rows. So the fastest that we can, the faster we're able to remove rows, the better. Having multiple tags, multiple pieces of information inside of our index. Maybe, I don't know if I have space. I'll just come down here to a blank spot for now. What happens if we have multiple, the trade-offs of multiple column indexes, trade-offs? The first disadvantage is that more columns means that we're storing more data. So more disk space being used. Closely related is that more columns means more data per row, more data per row, which means that there are fewer rows per index page table, fewer rows per index page table. So recall that the index page table is 8 kilobytes, just like the heap page table. And so if we're storing more information per row, we have fewer rows that we can store in an individual page table. And the number of rows is what determines the fan out. Number of rows per page determines the fan out. Which we use the letter B to indicate. And the total number of pages accessed that was theta of log base B of n. And so here, the total number of rows per page determines the fan out of B. What in particular is going to happen is that B will decrease. B will decrease. Because B decreases, because our fan out decreases, because the base of our logarithm over here goes down, this number over here goes up. So the total number of pages accessed will increase as we add more rows to the table or more columns to the index. It's still logarithmic, so the effect isn't too serious. But one of the things that we saw maybe 2 weeks ago now is that if you have an extremely large table, something like a trillion rows inside of it, that's going to typically result, if you have one column of big ints, that will result in only 3 page accesses to figure out how many to find the appropriate value. But here, if the B value goes down, that can go from 3 page accesses to say 30 page accesses, which is still a small number, but that would be a noticeable slowdown. So these are not like major, these are not major problems here, but they are small problems. The advantage here of actually being able to use the index and get the logarithmic access is way much better than these negatives down here. So the logarithmic access from being able to use a table or from being able to use an index offsets these disadvantages. But it does mean that you don't want to just add extra columns that you don't necessarily need. This sort of information right here is not going to come up in these free response SQL questions at all on the final exam. It's not something that you need for the homework assignment, but it will come up in the true or false sort of questions. I think even in the sample true false questions I have, one of the examples is if you add more columns, then the total number of pages accessed during an index scan will go up or down. And the answer is that it will go up because of this reasoning here. Did that answer your question, JP? Good question. Any other questions so far? Okay, the last thing about this problem 5 right here is our group by on id users and the aggregate function count over here. Because the group by is happening on id users, we need an index that's going to take id users into account so that we can do the group aggregate. And we already, as part of our create index for the joins, we're creating an index on get users. And so Postgres will potentially be able to use the group aggregate instead of the hash aggregate, combining those two things together. So there's nothing special that you need to do here for the group by or the count star up here. And so these 6 indexes, removing the duplicates, would be the full credit answer to this problem. In general, on any of these problems, you would not be required to provide any explanation about what your indexes are. If you choose to provide an explanation, then that gives you opportunity for partial credit if you get the wrong index but had the right idea. It also gives you the opportunity to lose credit if you write something that's just not true, then you will lose credit. So if you choose to provide explanations, then make sure that your explanations are true things that you're stating. Question?
I mentioned before that some of these are duplicate indexes that we call like one set or the other based on which method. Like what would we run?
So the question is what to actually write for this problem. And the answer is that you have to first figure out what are all of the indexes that you might need for any possible parenthesization here. So you'd have to first figure out that you need all 6 of these indexes. And then you can remove duplicates. So like down here, create index on users, id users appears twice. So you don't need to write out that create index command twice.
It's like anything that you might need to write it.
So yeah, if you wrote out these 3 up here, that one, that one, that one, and this one right here, those 4 lines would be a full credit answer. Does that answer your question? Question, JP?
Yeah, so that if you start writing
This first green one?
well, this,
This one?
yeah, because that one is when you do show.
Yeah, so we don't know how Postgres will choose to write these parentheses. The join operations are associative, so Postgres can do the join in either way and we'll get the same results. And even if you manually specify the parentheses, Postgres will ignore what parentheses you put and use its own internal algorithms to find the optimal join order. Since we don't know the optimal join order, we have to provide indexes for both possible join orders. So that's why we need not only the top one, but the bottom as well. Okay, coming back over to the notes for a second. At the bottom of this notes file, there's a section down here on parallelism and how Postgres will automatically parallelize your queries. You don't have to know any of this for the free response stuff, but there will be some potential true false questions related to this. And so these are the references that I'm expecting you'll be able to look things up here for Postgres. In general, it turns out that in theory, all SQL queries can be parallelized. In practice, due to various limitations of Postgres, they can't all be parallelized at this point. And so people are working on that, but I might ask questions about whether a certain query can be parallelized or not, and you'll have to look at the docs here to figure that out. Last concepts down here. So we've talked about multi-column indexes. An expression index is an index with a function in it. We've talked about that. Let's talk about partial indexes next. What is a partial index? Let's come back over here and take a look at, we already talked about problem 2 previously, but we'll rethink a version of problem 2 that can use partial indexes. For your final exam, for the free response here, and for the your homework problems, partial indexes will not come up. This is another thing that is true, false only. in a partial index, what it looks like is if you had a command that looked like create index on, and then the tables say users of id users like this, and then you add a where clause to the index where username is, say, greater than or equal to A, and username less than B. This right here is what makes the index partial. The where clause is what makes the index partial. And the first, the disadvantage of a partial index is that these values over here, this A and this B, are hard-coded values. And so you can never use a partial index with a query where the information over here is provided by the user. Can't use a partial index when the query conditions can change. Because you have to know what these values are at the time of constructing the index. So you can only use the partial index when these values are fixed. That's the disadvantage of the partial index. The advantage of the partial index is that we no longer have to store the username information inside the index itself. The advantage is that we're not storing whatever the condition information is down here inside the index, not storing extra columns in the index. So all the disadvantages we talked about with the multi-column index, none of those disadvantages apply. None of the disadvantages of multi-column index apply. I don't know if I've used this abbreviation IDX for index before, but that's a very common abbreviation. So if these values right here were hard-coded and not something that were user specified, then it would make sense to use the partial index, and it would only create the index, only insert rows into the index if it satisfies those conditions. Any questions about the partial index? The last concept down here is a unique index that has this include statement inside of it. This is something that you're not going to need it for the homework, but it will possibly show up on the free response. Here, let's consider a new problem related to this users table up here. That so that we have right now a unique index on the id users column right here. But let's say I wanted to run this SQL query. Select id users and created at from users. And we'll add a where clause, something like where id users equals some number. At this point, we can do an index scan on this query. An index scan can be used to solve this query. And that'll be very efficient. But we can do an index scan because the primary key up here creates a unique index on id users. Our where condition down here matches the index for that unique index. And so we can scan that unique index. This is not the most efficient thing that we could do though, because we still have this created at column over here. And in order to get the created at column, we'll have to actually reference the table. So we cannot do an index only scan. Ideally, we would have another index that looked like create index on users, id users, comma, created at. And this would allow an index only scan. The index only scan. Because now both of these columns are contained inside of the index that we're searching for. And so we can do an index only scan instead of an index scan. The index scan is still going to be fast, but the index only scan is faster. And so if we were running a web page where we really care about getting the information to the users quickly, we try to make everything be an index only scan. The downside of this index right here, though, is that it duplicates a lot of information from our unique index. So we're using a bunch of extra disk space. Uses lots of extra disk space. One idea on how we could solve that is by deleting the unique index that we have on users and making this index right here be a unique index. But if we make this index right here a unique index, it won't be unique just on the id users. It'll be unique on the combination of id users and the created at time. What we need is something that is unique just on id users, but not unique on created at. And that's what the include keyword gets for us. If we say, create index, create unique index. On users, id underscore users, include created at. Now we have one index that has both the information, both the id users column and the created at column. And it's enforcing the unique constraint on id users, not including the created at in the unique constraint, only including it in the index for the purpose of the index only scan. So this index right here would be the optimal index for a select statement like this, where we have to enforce a unique constraint on the id users. This red index, again, is acceptable, but it duplicates information in that unique constraint, and so we would need two indexes, the unique index and this created at index. This green index down here allows us to do it with just a single index. Any questions on that include operation? Okay, then that is everything about the generic btree indexes or indexes in general. And we'll move over to the topic 11 folder, wherever that went to. Topic 11, which has information specific for, so more advanced indexing, indexes for full text search and for JSON search. So you'll need this information here for completing the denormalized portion of your homework assignment. And then the full text search up here is for completing the last 2 queries in the homework assignment. The first 3 queries, you should have all the information that you need. There's 4 types of indexes that we're going to talk about: a hash index, and then scrolling way down here, there's the gin index, the rum index, and the gist index. We'll probably not get to the details of those today. We'll do that on Friday. And we'll start today with a generic overview of this section on difficulties of full text search. So we'll see exactly what we mean by full text search, why the btree can't handle full text search, and then the next time we'll talk about these other indexes that solve this full text search problem. Okay, so we've seen some simple queries like this before, where we have just a no joins, nothing fancy, just a select from table and then a where clause. But we want to zoom in on this like operator here and queries that make the like operator fast. In this case, we have 2 of these glob operations, 2 of these percent signs over here. And so this query is going to match the word corona as long as corona is contained anywhere inside of the text of the tweet. But a btree index is not going to be able to speed this up for us at all. It turns out that if we had a single wildcard, so something like this, then we could use a btree index for that. The reason is because this query right here can be translated back into this query right here. These 2 things are exactly equivalent to each other. Having the glob percent sign right here again matches any string of text to the right, and by the ASCII-betical ordering of strings, anything that is greater than or equal to corona and less than or equal to coron b will match this query up here. And because things are stored alphabetically on the column, we've seen that we can, with the btree index, match range queries like this efficiently. So the key difference between this up here and this down here is that we have just 1% sign over here at the end of our string query instead of 2% signs up here. If this percent sign was at the beginning of the query, there would be no way to make the operation fast. So it's only the percent sign at the end that allows us to rewrite it like this and make the operation fast with the btree. Another sort of aside is up here, we're using the like operator. And again, in Postgres, like is case sensitive. If we use the I-like operator, case insensitive instead, then we would not be able to speed it up with the btree index. The reason for that is the case insensitive version is like all of these or statements concatenated together, whereas we have every sort of possible combination of case sensitivity here. And so this turns out to be exponential in size, and so not something that can be sped up with the btree index. Other databases don't allow or make the like operator case insensitive, make it behave exactly like I like. Postgres sticks with the SQL standard, making like case sensitive because of this performance implication, and so that you can still speed up queries using a btree index. So that's what that section up there is going over. In your homework, there is a SQL query that looks something like this. And so the best way to speed this up would be a btree index on the tag operation right here. And that will let you speed that up. We'll talk real quickly about full text search outside of Postgres, and that'll be it for today. So it turns out there is no SQL standard for full text search. And most full text search systems are not SQL based. They're one of the reasons NoSQL became popular is to handle this full text search. So basically to be able to handle situations like this up here with the percent sign on both sides is one of the reasons NoSQL databases became popular. Elasticsearch is currently the most popular open source-ish full text search engine, but again, can't be combined with SQL queries at all. I think one of the main disadvantages of it is that it requires installing another full service. So even though Docker Compose and Docker make this relatively easy, it's still a lot of things that you have, a lot of extra complexity that you have to deal with. And the advantage of keeping things inside of Postgres is that we won't have to deal with this complexity. Turns out that Elasticsearch is not open source anymore. It was originally licensed under Apache 2. The company, is a $2 billion company, had their own hosting service called just Elasticsearch as well. Amazon saw that Elasticsearch was extremely profitable, and so they just cloned Elasticsearch as an AWS offering. The Apache 2 license allows you to do that. You're allowed to do whatever you want with the product. And so Amazon was not in violation of any of the licensing agreements here. But this completely undermined the Elastic company. Their market cap or their stock valuations like halved overnight when Amazon made this announcement. And so in response, Elastic relicensed their software to what's called the SSPL license. It was first created by MongoDB. And the basic idea of the license is that you can do anything you want with the service except allow other people to pay you for hosting it. And so it's specifically targeted just to prevent AWS from hosting MongoDB and Elasticsearch instances. This is technically not an open source license according to the OSI group because you're not allowed to do whatever you want with it. You are allowed to look at the code, inspect it, modify it however you want, but you can't run the code however you want. And so Elasticsearch no longer considered open source. This is a good stopping point for us today. Next time, again, we'll see how to do these full text search queries in Postgres. It's not a SQL standard thing, but Postgres has the best support out of all the SQL databases for this. Elasticsearch, though, a little bit better support than Postgres. If anybody has questions about anything, I'll stick around after class and get those answered. Otherwise, that's it for today. You're welcome.